Section 2.5, it's about continuity of a function. So when we say a function is continuous, this means it's like the first figure you see on the left upper corner. There's no jump or gaps or holes. That's called continuous, like you don't lift your pen or pencil off the paper. For an example, not continuous, like the middle graph in the first row, this is not continuous, it's called discontinuous. So another way to say not continuous, discontinuous, because there's a hole there. And specifically, that's called removable discontinuity. Removable discontinuity. For the last one on the right-hand side, that one is discontinuous because there's it's specifically called infinite discontinuity because there's kind of like a jump in there. That's what it is. So at x equals, let's say a, it's discontinuous there. That's called infinite discontinuity. Now the next one, this is a function that is being drawn this way. This is called jump discontinuity. Jump discontinuity. How to prove a given function is continuous. That's the big question we're going to answer in this section. The way I define it, we say in order for a function f to be continuous at a point x equals a, this condition needs to be met, that the limit from the right side of a equals the limit from the left side of a equals f of a. So that proves to us if all these are met, then the function is continuous at x equals a. That's what it is. So continuity at a point means if you can prove the function is continuous at every single point, hence it's continuous. And we are here emphasizing the fact about the function is continuous at x equals a. So if we look at an example, this is a piecewise function. Is this function continuous? Well, in general, we know this straight line is continuous and this parabola is continuous. But there's some restrictions here. These are restrictions. What happens at x equals 1? Do these two graphs meet at 1, or there's a hole in there? There's some kind of discontinuity. Okay, so that's what we need to see. What happened at x equals 1? Do they meet? Are they okay? So in general, if we can prove that this function is continuous at x equals 1, then this function is continuous everywhere. So to do that, we apply the main definition here, is that we find the limit of this function as x approaches 1 from the right side and the left side and at 1. And let's see if they are all the same. So from the right side means a little bit above 1. We use the second equation, which is x squared minus 4. So if you substitute that in, you're going to get 1 minus 4, which is negative 3, or if you pass the limit. And the same thing for 1 minus, that would be for the first graph, because it says use the first one, the 2x minus 5, when x is less than or equal to 1. And that's what I did here. It would be 2 minus 5, which is negative 3. And then the next one is f of 1. F of 1, that would be 2 times 1 minus 5, which is negative 3. Notice they're all the same. So this means since the limit from the left, the right, and at 1 are the same, then we say the function is continuous at x equals 1 and hence continuous. Another thing here, as another example with a different format, find the number or numbers at which f is discontinuous. So what do we always do? We look at these conditions here. So at x equals 1 or at 4, what happens? Well, we need to check if this function is continuous at 1. And then we need to check also if it's continuous or not at 4. So we start by finding the limit of the function as x approaches 1 from the right side. Right side means a little bit above 1. And that would be the second line, which is the 3 minus x. So 3 minus 1, which is 2. If you do from the left side of 1, that would be the first equation, or 2 to the x. So 2 to the first power, which is 2. Also, f of 1, that would be the first line, or the first function, sorry, which is 2 to the x, 2 to the first power, which is 2. Notice they're all the same. Therefore, this function is continuous at x equals 1. If we do 4 plus 4 from the right side, 4 from the right side, it would be the last one because that's a little bit above 4. So we pass the limit as x approaches 4 plus of that equation, the square root of x, which is 2. And if you do it from the left side, that would be the middle equation, 3 minus 4, negative 1. They're not the same number. They're not equal. So we can say that the function is discontinuous at x equals 4. Now we got some facts. What are the facts that we have? So if we have two functions, f of x and g of x, both are continuous at a point x equals t, and k is any constant, any number, then all of the following are continuous at the same number, x equals t. What are they? The sum of two continuous functions is continuous. That's what it's saying, f plus g. The difference of two continuous functions is continuous. F minus g is continuous because both f and g are continuous at x equals t. Hence, their difference is continuous at t. The product is continuous at t. The quotient is continuous at t. Any constant times a continuous function at x equals t is also continuous at x equals t. We also have that all polynomial functions are continuous. Any polynomial function. Rational functions are continuous over their domains. The same applies for exponential, logs, and trig functions. And to see how to apply this, if we look at this example, is this function continuous? We're not going to graph it, but instead we're going to look at this one. The first thing is x squared is continuous, so this one is continuous, and e to the x is continuous. Hence, their sum, the top sum, is continuous. The bottom one, the x squared minus 4, it's a polynomial function. This is also continuous. Therefore, their quotient is also continuous. So x squared continuous, ex continuous, their sum is continuous. The denominator is continuous everywhere except at 2 and negative 2. Therefore, this function is continuous everywhere except at 2 and negative 2. We got a theorem here about composite functions. So we have, if f is a continuous function at x equals b, any real number b, and the limit of g of x is, as x approaches a, is b, then we have that the limit of the composite function f of g of x is really f of b as x approaches a. Because we already know, in other words, you can pass the limit inside. This can go inside. That's what we did. And this thing here is given as b. That's why this is f of b. So in other words, you can pass the limit inside to the function as long as the main function f is continuous at that point, at x equals b. If it's not, then we're not allowed to pass the limit inside a composite function. An example in this, if we are allowed, or if we are asked to evaluate the limit of arcsine or sine inverse, of 1 minus square root of x over 1 minus x. What do we do here? Well, we can pass the limit inside. Why? Because arcsine is a continuous function over its domain. So that's why we were allowed to pass the limit inside. But then this thing here, if you try to evaluate the limit, that will be 0 over 0, which is indeterminate. So then the way to get rid of the 0 over 0 is rationalizing the numerator, 1 plus square root of x over 1 plus square root of x. On the top, we get 1 minus x, and the denominator stays the same. So you can cancel 1 minus x away, and that would give us arc sine 1/2. Arc sine 1/2, what is the angle? It's sine 1/2. It's pi over 6. So in general, to summarize this section, a function is continuous at a point, let's say x equals a, if the limit from the right side, left side, and at that point are all the same, then we say it's continuous at x equals whatever that point is. So that's what continuous functions are about, and we're going to be using them later on in some of the subsequent sections in this course. But it's important to understand what continuous means, what a function, what is the definition of continuity. Means the limit from the right, from the left, and at that point, they all must be the same in order for the function to be continuous at that point. And when the function is continuous at every single point, then it's continuous.